common ion effect. Okay, we will be talking about the common ion effect with solubility. It's a very valid one. What else?
Ionization.
Percent ionization, did you say? So percent ionization will probably be on your free response. That's valid. What about this multiple choice right here?
KSPs.
KSPs, mass volume percent. We're going to have titrations. Okay, so those are a couple of the things we have to do. Recognizing titration graphs. So let's start off with something like that. Corb, will you put this middle one down? Let's start off with that problem, and then we'll go into this problem. Because what's another topic I didn't say? Buffers. Buffers will be on your test. Understanding what a buffer is, okay? And we'll talk about that right now. To start off, let's answer this question. Which graph that I've written here, okay, which graph best depicts, best being maybe a word I should have underlined, the titration of hydrochloric acid with potassium hydroxide. So, the titration of the acid by adding the base. Okay? Take 2 seconds, look this over for just a minute or so, and try to figure out the best answer. Can everyone see it okay?
Yes.
Okay. Try to draw the lines kind of fast. So, number one, when we're looking at this, we got to understand what the titration is. I have acid, and I'm titrating it with a base. That means, what should my initial pHs be if my acid is what I start with? They should be pretty acidic, right? And as I add base, I should be moving towards my base. What's another thing we can look at? It's very important to understand which acid am I starting with, a strong or a weak. In this case, this is probably the most common strong that we talk about, hydrochloric. So I know that the pH of my starting solution should be high or low? Low. And low respective to like other acids that may be weak. This one should be around 0. Okay? So as I look at these, I can immediately rule out 2 of them. What are the graphs I immediately rule out? I rule out C and D because that would be the opposite thing. That would be starting with the base and adding acid as we titrate. So I rule these out and say it's not these. I come over here and I say, okay, we said that it should be a strong acid, so it should start at 0. Both start at 0. So we have to find other means by deciphering which one is probably the best. What are we titrating with? KOH, strong base, which means once we pass our equivalence point and all of my acid is consumed up in my titration, right, I should approach the pH of the titrant, right, of the base. If it's a strong base, I should approach the pH should be pretty high. In this case, which one looks like it hits the highest pH mark?
B.
B. And B is the correct answer, okay? So, good job, you guys. One thing to understand, we've talked about this in my recitation, right? When we do a titration, it is crucial that you understand it doesn't matter if both of them are strong or one of them is weak. The idea is the exact same, meaning if I have 5 molecules of base, I need to titrate that with 5 molecules of acid. I don't care if this is a weak base. I know that if it's a weak base, not all of those 5 molecules will probably act as a base. Some of them will hold on to the hydroxide ion. But that doesn't matter. I need to still account for the possibility that that will happen. So when I do my math for my titrations, just know that I always will have the same amount of moles to titrate the exact same amount of moles. Whether one is weak and strong, that doesn't matter. They just need to be the same amount of moles, okay? So don't let that confuse you. If you take a weak acid and titrate that with a strong base, the amount of moles need to be the same. That being said, if I had a weak acid and I titrated it with a strong base, right, my equivalence point will be variably according or around 7. You know, compared to 7, where will it be? Above 7 or below 7? I have a weak acid and a strong base titrating my weak acid. Once I hit equivalence point, where might pH be? Above 7. Right, exactly. And vice versa would be below 7 if I had a weak base and titrated with a strong acid. Okay, that's good. Let's move on to this one real quick. And we need to sort of hustle through these problems. Okay.
Great, so just in terms of that last question, so in there the HCl was the analyte and the KOH was the titrant.
Yes.
Correct? Okay.
Good. The lingo can be difficult, but yeah, the titrant is what I am adding to the titration to analyze what's going on. Is the titrant. Yeah. Okay, what we need to do, you guys, is sort of hustle through some of these first problems because Corbin is going to do a full titration, which is kind of like the meat and cheese of like everything we've been doing. So it's really important we give them plenty of time to do that. Meaning we need to hustle through some of this a little bit more. Okay? So let's do this problem. What is the final pH of the solution made by mixing 100 milliliters of 0.05 molar acetic acid with 100 milliliters of 0.1 molar sodium acetate? So what is the final pH of this solution? Work on this. Okay, one thing is whenever we do these problems, we definitely need a few values. One of them being a Ka, right? We definitely need a Ka for this value, for this problem. We are using acetic acid. Has anybody done enough problems that they can tell me right now the Ka of acetic acid?
1.8 times 10 to the negative fifth.
He's got it. 1.8 times 10 to the negative 5. That's a good thing. If you can look at problems without having to look at a Ka and say, oh, I know the Ka of that. That's a good sign because you're doing plenty of problems. So he's right. I'll write it on the board. The Ka for acetic acid 1.8 times 10 to the negative 5. So take 2 seconds to look at this problem, and I will put up kind of how we're going to do this. Okay, guys. So when we read this, we see that we have one of the pH of the solution. Inside of the solution, I have my acid, but I also added something else. I added sodium acetate. Sodium acetate, is it soluble? How do I know that sodium acetate is soluble?
Sodium.
Because everything with sodium is soluble. Plus, it goes right along with my strong base rules. You know, sodium is right there in the first 2 columns, so it has to be soluble because sodium hydroxide is a strong base. So sodium acetate will dissolve completely. So I have a certain amount of moles for each. There is a way I can solve this equation, or this problem immediately with an equation. What's the name of the equation I was using to solve this problem?
Hasselhoff.
The Hasselhoff equation. Yeah, my friends call it the Hasselhoff equation.
I can see that.
But yeah, it's the Hasselhoff, which is pH equals to pKa plus the log of my base over my acid. Right? Now, what do I need to do here?
You need moles.
Right, I need to put it in moles just to be safe, because I am adding a few different amounts. It looks like I have 100 milliliters and 100 milliliters. Well, in this case, I have the same amount of volume, so I could probably get by just with molarity. But I need to figure out the numbers in moles of base and my numbers in moles of acid. Okay? And you guys should know how to do that. That's something that you should be really familiar with. I'll plug it right into this equation, take the negative arc my Ka, and get my pH.
You can't do that in molarity?
You can do it in molarity. You can.
You can do the molarity even if the volumes were different, right?
Can't we just plug
You know, I haven't done a problem like that in a while, so I would just do it twice to be safe. Make sure you get the same problem. It should be the exact same, but I like to just like standard always use moles, because moles seems a little more exact, but more its concentration is probably
In what situations can you use this equation? Because usually, like, we use it after we do the VA table, like with the titration.
good question. The situations in which you use the Henderson-Hasselbalch equation will always be the same. It is a situation in which you have some amount of your acid and only present in the solution as well another amount of your conjugate base that comes directly from that acid. If those 2 things are present in any degree, one could be a lot more than the other, it doesn't matter. As long as those 2 are present and we don't have like more OH minus in there, as long as it's just those that are left over, like in this case, that's what I want to know to use my Hasselbalch equation, right? Now, in titrations, there will be cases where I do need to use the nice table, right? But not at any moment when I have both my acid and my conjugate base together. Because it's these values that I need to be able to do the problem. When I do this out, guys, I get that the negative log of this should be, let's see, 4.76. And when I plug these numbers in, right, I basically get this plus the log of 2. And when I do this math out, I end up with a pH of 5.06. So hopefully you got that, okay? So this is buffers, and buffers aren't going to get any more intense than this, meaning I'm usually using this equation. I'm just trying to figure out what is the buffer, what is being put in there, okay? So, go ahead.
Why don't you have to use a bot table?
A what?
A bot table?
Oh, a BAA table? Well, you don't have to use a BAA table because this is so much easier. You just have your acid and your conjugate base. If you use the BAA table, let's see, doing that, you would be able to find your H plus, and then you could still get your pH, but you have to do you wouldn't really do a BAA table, you do an ice table. It would take so much longer, whereas this is so much faster. Right? What I would do, it's like some of these things you come on to see we do, you guys, there are just equations, and we just say, this is the equation that helps you get this. And it's kind of one of those moments where I'm just saying, know that this is the equation you used. You could do it another way. This is so much easier. So,
You said flammable areas before we should direct to moles in this equation. That would be safer bet.
well, I think it's always a safer bet. Yeah. But most of the time, it won't make any difference. Yeah. I just haven't done a problem in a long time where they gave like different amounts of volume of each, but the molarity should be fine. Yeah, it should work out. Okay. All right. So let's move on quickly. Let's do this one right now. Okay. The solubility product constant for magnesium fluoride is 6.4 times 10 to the negative 9. How many grams of MgF2 will dissolve in 150 milliliters of water at 25 degrees Celsius? Okay. This is a very normal solubility problem. Okay. Look this over for 15 seconds. Try to get it in your mind the first step you're going to do to solve this problem. Right? And then let's do it really quickly and maybe pass the baton to Corbin. Just a couple minutes. Okay, so what is the first step in solving this problem that you guys noticed? Yeah.
Roger's dissociation reaction.
So it's a dissociation reaction, right? This is a KSP, so it's some sort of salt. I'm dissolving it, so I'm getting my conceptual understanding of what's going on. Obviously, I know that it's not 100% soluble. I wouldn't have been given this, right? So immediately I know that I can use some sort of ice table, right, for dissociation constants, and try to solve for my molar solubility of this. What's specific about this problem that maybe tweaks it and makes it just a little bit harder is the fact that it is MgF2, so it's not a 1-to-1. We're going to do the table out so we can see this. And again, they also told me they want to know how much mass of the whole thing can dissolve in only 150 milliliters of water. So there's these little variables that kind of throw us off a little bit. But let's start with what we know. Let's write the equation out quickly. We get this, right, breaks up into that plus 2 at 9, which is what you guys said, which is good. To catch up, we do our rice. Okay, so here's this. We need to know our initial concentrations. Okay, so what's our initial concentration of our solid here? Who cares, right? That's what Dr. Macedoni wants you to think. Who cares? It's there. That's all I care about. Let's just get rid of it, right? It's there. I do know that the concentration of it that I'm going to lose is going to be this little amount here, right? This is my molar solubility. This is important. This is how much will dissolve. But the whole rest of this I don't really care about. Started off with how much of this? Actually 0 and 0 of this too. Now, someone said earlier the common ion effect. All that is what if I said I put this salt in a solution that already had a little bit of magnesium ion? Well, then that would be initial right here. That's all that will change. That's the common ion effect. Other than that, this process is the exact same. Okay? This case, it's a little bit easier. This will gain a small amount. This will gain how much? Not just x, but twice as much, right? 2x, come down here, equilibrium will be x. When I write my expression, I'll get x times 2x. What's important here? A lot of people forget? Squared. That is a common mistake. It is equal to 6.4 times 10 to the negative 9. Okay, so a lot of people make the mistake right here also doing this math. What I need to do is this square is just for this. So what is 2x squared? 4x squared times x. 4x cubed. Okay, perfect. You guys got that. 4x cubed. So this should be 4x cubed is equal to 6.4 times 10 to the negative 9. How do I solve for this? Just make it easy. I will divide by 4, right? And then once I do that, I'll get x cubed is equal to 6.4 times 10 to the negative 9 divided by 4. And then I take the cubed root. If you don't know how to take the cubed root in your calculator, raise it to the 1/3. Okay? That tells me what x is equal to. When I do that, I get x is equal to, let's see, 0.001196. That's what my X is equal to, right? And what does this tell me? This is my molar solubility. This means that for every 1 liter of water, 0.0011696 moles of this dissolve. Well, that's this X right here, right? We want to know how much of this will dissolve in only 150 milliliters. So if this is for every 1 liter, I need to know how many moles for every 150. So this is for every 1 liter. I want to know for every 0.15 liters, because I want to know every 150 milliliters. So when I do that math out, I didn't do that part, but I can write the number down. I can do it real quick. 0.15 times 0.0111696. Okay, I will get that for every 150 milliliters of water, I dissolve 1.754 times 10 to the negative 4. Right? That's moles. I want to know grams. I could have stopped here if they said how many moles of MgF2 dissolve in 150 milliliters of water. That would be my answer. This is in moles, right? Well, now I need to just get it into grams. So how do I do that? Just got to get the molar mass. When I do that, add it up, I get 62.1 grams per mole. When I convert how many grams is this many moles, I should get that it is, did anybody do it? 1.08 times 10 to the negative 2 grams dissolve of MgF2. Okay. This is a good problem. This is a problem that integrates a couple things you learned from Chem 105, makes you think a little bit, puts you on your toes with something like this. But it is not considered a difficult KSP problem. So if that's difficult, that just meant that you just need to practice a little bit more, because you guys have been doing things that are more difficult than this, but maybe aren't as familiar. So I know we just started KSP, but this is a problem that you guys should feel pretty comfortable with, okay? So let me answer some questions before we kind of turn it over to Corbin to do the big titration. And then if we have time at the end, I have like a couple more problems we can do. And if you guys don't have class after this, please come up and we'll take 30 minutes or so and answer your individual questions, okay? So questions about this specifically before we move on to the titration. KSPs, yeah.
Where did the 6.4 times 10
So the 6.4 times 10 to the negative 9 came from my solubility product constant. So this KSP is just like a Ka or a Kb or a Keq, right? It's my equilibrium constant for this specific solvent. Again, common ion effect would have only changed what I put up here, right? And then would have changed what I put down here. If I had a little bit, like if I had 0.1 molar already in the solution, this would have been 0.1 molar plus X. That would have just changed all of this math. Okay? But I still would have solved for X and still would have figured it out just normally. Okay? Ready, Court? Okay, guys. Last question, I guess, what is the difference between molar solubility and solubility? Who can tell me that? They are different. This is important. Mattson.
Yeah, so molar solubility is how many moles can dissolve in however much
Perfect.
solution we have.
Okay.
And then solubility is referring to how many grams or milligrams, depending on
What they ask for.
specify.
Right. So solubility is a mass amount in grams, kilograms, milligrams, whatever, per liter of water. That's solubility. And molar solubility is exactly that. How many moles? It's important to distinguish those because he might just ask you what is the solubility, not hint you that it's mass. So make sure you have those distinguished. Okay?
Okay, titrations. We know titrations, they're kind of this big monster in the class. The thing about titrations is once you kind of understand the science of it, it basically becomes automatic. Once you really understand conceptually what a titration is and how it works, it should be like you guys' go-to. You shouldn't miss any problems on titrations. So what I want to do first is I was just kind of thinking about titrations myself, and I thought about a few principles that I usually go through in my own head as soon as I encounter a titration problem. So if I was you, I'd write these principles down on your notes. So number one is what is the equivalence point? Okay? So let's look at this problem I wrote. And I'm going to do this, we're going to do all this math out. So what I would do is follow with me in your notes, write down everything that I write on the board. So you can go back later when you're studying for the test and think through all the steps that we did together in the review. So number one, what is the equivalence point? For moles and liters, okay? So when something is completely titrated, like Braden said, it's when the in this case, our acetic acid, it's when our acetic acid amount of moles equals our strong base moles that we're adding. That is the equivalence point. So what I want to do first is figure out, well, how many moles is that? How many moles of strong base is it going to take to completely titrate this weak acid that I have? Okay? And number two that I want to figure out is how many liters of that strong base is it going to take? So when I encounter problems where they say 10 milliliters of titrant was added, once I know how many liters of my equivalence point should be, then I know exactly, okay, that's before my equivalence point. And this gets into our next little hints and help guide for titrations. Anytime you do a titration and you're before the equivalence point, you're going to use the Henderson-Hasselhoff equation, okay? Because I'm going to show you when you're before the equivalence point, you're going to have only weak acid left in this case and its conjugate base, okay? So you're going to have acetic acid and acetate. And when you have that situation, the simplest way, like Braden said, is to just Henderson-Hasselhoff it. Okay, the pKa, and then you got it. Super simple. Next, at equilibrium, what you're going to do, you're going to do a BAA table, and then you're going to do an ice table. Okay? And like I said, I'm just going through these quickly. We're going to do it all together. If it's after the equivalence point, what you want to do is you're going to have leftover strong component left. You're going to have leftover strong base or leftover strong acid. What you can do is just calculate the pH straight from that. Typically, that's what the pH is going to be. You are going to have some leftover conjugate base or acid, but typically, and I'm saying typically, it's so minute that it's really not going to affect the pH at all. So if you want to be really thorough with that conjugate that you have, run it back through an ice table just to check yourself. But usually the pH of the strong component is what it is, because the weak component is really not going to do much at all.
And I recommend always doing the last step, even though you'll see that it doesn't change much, because if it does for some reason, maybe that indicates that you did something wrong, or maybe it's a special problem. So do it, but Corbin is exactly right. A lot of times it doesn't affect anything, but I would still do it.
Okay, so I made this problem. So I've got all my work right out here. It's kind of a lot of math, so bear with me as I'm looking at my paper and figuring out exactly all the calculations I did. So what I have here is I'm saying a titration of acetic 0.23 molar acetic acid, 25 milliliters of it, and strong base, 0.0076 molar KOH. So to understand this, what I have a little beaker of acetic acid. Okay? What I'm going to do is I'm going to add KOH to that. Okay? So come back to our steps. What's the first thing I'm going to do? Find the equivalence point. Okay? So I have 0.23 molar acetic acid. And I'm trying to figure out how many moles that is, right? I know how many milliliters I have. I have 0.025 liters. And this is X moles. Okay? So multiply that out. Your moles is going to be 0.00575 moles. Okay? This is going to be really important. You're going to be coming back through this whole titration and referencing these two numbers that we're doing. Okay? Now the second thing I want to do, I want to figure out what's the equivalence point, how many milliliters of KOH am I going to have to add to get 0.00575 moles, okay? So there, I know I have 0.0076 molar KOH, and I know I need 0.00575 moles of it. How many liters is that? And when you do it, it's 0.76 liters. Okay. So I'm well on my way to the titration. I figured out how many moles and how many liters I'm going to have to add of KOH to completely titrate this.
Can I just add, does everybody know how to do that step? Because I don't want you to feel like, well, I guess everyone else knows, so I'm not going to ask. That is so important what he just did. Do you all know what he did? Because there are several ways. You can do it his way, which is just as right as some of you just memorize C1, B1, C2, B2. Do we have, the general feeling is yes, we can always solve for that. That's very important.
Your main
Yes.
equation is molarity equals moles per liter. If you just use that equation, you can plug in whatever you need and solve for your X.
Okay.
With the C1, V1 times C2, V2.
It's the same thing he just did. He just split the two into two sides. Yeah. Exactly.
Okay, we good? Let's start it. So, my first question is, what is the pH of my solution before I add any base? Okay? This is something that we've done so many times. This should be basically automatic to me. What am I going to do? Rice table. Okay? So my initial concentration of acetic acid is 0.023.
It's 0.23.
Oh, sorry, 0.23. Okay, water doesn't matter. So this is going to be minus x, 0.23 minus x. I have 0 of this, plus x, x, and x. Okay? So now you're going to want to set up your expression. Okay? I'm running out of room here. So it's going to be your Ka, 1.8 times 10 to the negative 5, is going to be equal to x squared over 0.23 minus x. Okay? Solve that out. X equals 0.00203. And this x equals my OH minus concentration. Right? Because that's, or sorry, H3O plus. Okay? So then I take the negative log of that, I'm at my pH. My initial pH, if you do it out, should be 2.69. Okay? That one's super simple. Let's go on. Any questions on this first step? Initial pH?
Because that's your regular ice table, so you guys should be really familiar with that one.
Okay. So now what I want you to calculate is what is the pH after I add 120 milliliters of KOH. First thing in your head, is this before, at, or after my equivalence point? Before. Okay? 120 milliliters is 0.12 liters. I knew that my equivalence point was 0.76 liters. Okay?
Good.
I immediately know this is before my equivalence point. So what am I going to do if you look at the hints?
To solve for a pH. No?
Yeah.
Both, yeah.
Yeah, you're going to do BAA table,
Choose
and then you can do the Hasselhoff, the easiest way to do these.
Good.
Okay, so we set up our BAA table. And what I'm saying here is I'm saying we have acetic acid, and the easiest way to write KOH is we know that's a strong base, so that's going to just be pure OH minus.
Because the K plus is a what? Remember the a spectator ion, right? It doesn't do anything once it's dissolved. So you can admit it and write a net ionic equation. Okay? So remember, BAA, what am I dealing with here? Moles. So, I already solved. How many moles of acetic acid do I have in my solution? 0.00575. I already solved for that. Okay? 0.00575 moles. Now, what do I need to figure out? How many moles of OH is added? Okay? This comes back, this is the way that I always do it. I do what's my OH molarity? 0.0076 equals X moles over how many liters? 0.12. Okay, does everyone understand this step right here? To find out how many moles of OH I added. This is crucial when you're doing titrations. The BAA table is always in moles. So I solve for my moles, and when I do that, I get 9.1 times 10 to the negative 4. Okay?
and I have, this doesn't matter, I have 0 of this to start. Okay? Now think about this. I have an acid and I'm adding a base to it. Okay? So this amount of moles is going to naturally go down. And what you do here is I take this, subtract this, I'm left with this. It's 0.00484. Okay? I had no acetate to start, but as I'm adding this base, this acid is reacting with the base and producing conjugate. Okay? So I'm going to have exactly as much conjugate base, moles, as however many moles of OH I added. Because for every mole of OH I add, that's how many moles of acetate I produce. Yeah?
Does this change for something dichroic?
Yeah. Yeah, you'd have to do it. You'd have to.
I mean, no, because all of our diprotic stuff, the second one really isn't strong. And also, I guess if they gave you a K, you would just redo the second spot. But in balancing the equation, if you were going to do a strong, you would have to account for the fact that it would take 2 OHs to take out to make the full conjugate base. So it would then be half. It would make half the amount.
I think you're going to see something like this, where you have a weak component and you're titrating with a strong component. It's typically what it is.
Mm-hmm.
Okay, so of acetate, I have this same exact amount of moles. Okay, so now I Henderson-Hasselbalch. pH equals pKa plus the log of base over acid. Now, what you can do, you can just do this amount of moles in this Henderson-Hasselbalch, or you can convert it to molarity. Either way, you're going to get the same answer.
So when will you add the OH in the acetic acid? Do you ever do that to bring it over to the basic side? Or
What?
the H2O side, the product side?
When you add, I'm sorry?
The 0.00575 and the 9.1 times to the -4. Will you ever add those?
No, I'm subtracting it because I have I have an acid that's reacting with a base.
Right.
So that acid, those acid moles are going to be lost and they're going to be converted into acetate moles.
Right, I get that you subtract, I get that. But on this side, you just write the same
On
number.
on this side it's always the same because for every mole of this that reacts with this, I produce 1 mole of this.
Okay.
And let me say one thing about this. The only time as well that you would have an addition with what you're adding is if this problem changed and instead of it being a pure acetic acid solution, we're titrating a buffer. So in a buffer, right, we have some acid and its conjugate base already there. And in this case, we already had some of this, so we would be adding whatever we did make more of it, we would add. So that's the case when we would add if we're titrating a buffer. In this case, it's the normal titration. So.
Okay, so when you do that out, you guys can do all the math. This should be pretty simple. Your pH should be 4.03, which makes sense. Our solution is getting more basic from our initial pH.
Did you guys get that answer already? Great. Okay, that's good. A lot of head nods. That's good.
Okay, so next one that we're doing, the pH at equivalence point. Okay, what's my first step? BAA. Okay. And how many moles of acetic acid did I start with?
0.005.
Same number, 0.00575. Okay? Now, at the equivalence point, how many moles of KOH did I add?
Same.
The same.
As
Exactly. The definition of an equivalence point is when the moles of titrant that's added equals the moles of analyte that's there. Okay? So I know I added the same exact amount of moles. Okay? And so water doesn't matter in this case. How many moles of acetic acid am I going to have left?
No.
That minus that is 0. Okay? I had no acetate to start, but how many moles am I going to have after the end? I'm going to have the same amount of moles, so 0.00575. And remember, this is in moles. Okay? What's the next thing I need to do? Get it into molarity. Okay? Yeah. This is where a really common mistake is made. You get this in moles and then you run it straight into an ice table, but that's going to give you a wrong answer. You have to calculate the new molarity of this acetate. So, the easiest way to think about this is how many moles of acetic acid, or how many milliliters of acetic acid do I have to start?
25.
I'm just calculating my total volume here. 25, and how many did I add?
You added 0.76.
0.76 liters, so 760 milliliters. And that equals 785 milliliters, which is 0.785 liters. This is a crucial step in your titrations. All I did was I added the volume of this to the volume of this that I added. And I already calculated that before I even started my problem, so this was super simple. Okay? After you do that, your concentration of acetate is 0.0073. Okay, now I have a concentration of acetate. Now what can I do? If you look back at our steps, your rice table, okay? So now I'm going to take this and run it straight through the rice table. So in a rice table, if you haven't seen by now, you're always taking what you have, adding it to water, and then seeing what's produced. Okay? So I have CH3, COO minus plus H2O yields OH minus and acetic. Okay. Some of you have probably seen what I need to do, what my problem is here. Okay? So my initial concentration of COOH is 0.0073. Water doesn't matter. Okay? This is familiar to you guys. 0.0073 minus x. 0, 0, plus x, x, x. Okay.
We need a KV value.
You need a KV value, right? This acetate is acting as a base, so I can no longer use my Ka value. I have to convert that to a Kb value. Your Kb equals 5.55 times 10 to the negative 10. Okay? And that is going to equal x squared over 0.0073 minus x. When you solve that out, x equals...
Can you assume that problem, you guys? 0.0073 compared to something raised to the negative